Welcome to the KCSE Paper 2 of 2019, Physics Paper 2 of the year 2019, and we go straight to the first question. What are we told in the first question? Let's look at it. We are told that the figure 1 shows two plane mirrors inclined at an angle of 120 degrees to each other. A ray of light makes an angle of 40 degrees with the first mirror. By completing the ray diagram, determine the angle of reflection on the second mirror. So when you study that diagram, we can be able to see this incident ray here strikes the mirror at this point. We should realize that what we've been given here is the angle that the ray makes with the mirror. Don't be deceived by that. That is not the angle of incidence. The angle of incidence is defined as the angle between the normal at the point of incidence and the incident ray. And this line here, since it makes 90 degrees with the mirror, it must be in the normal. And you can see it is drawn at the point of incidence. So this angle here is the angle of incidence. However, what happens to the ray? The ray, as soon as it strikes the mirror at this point, it gets reflected and it will move this way. And it will obey the laws of reflection. And this is how it looks like. So we need to determine this angle here as the angle of incidence so that we can use the first law of reflection, which states that the angle of incidence is equal to the angle of reflection. How do we define the angle of incidence? The angle of incidence is the angle between the incident ray, which in this case is this ray here, and the normal. So this angle here is 50 degrees. How do I get 50 degrees? I have to realize that by normal, we mean this line here, which is drawn at the point of incidence and referred to as the normal. It is referred to as a normal because it makes 90 degrees with the mirror. So, because the whole of this angle is 90 degrees, if I subtract 40 from 90 degrees, I get 50 degrees. And let's indicate those angles on the diagram. So it is important to indicate these angles on the diagram because this will help us to follow or to trace the direction in which this ray is moving. So we have already determined that this angle here, which is the angle of incidence, should be 50 degrees. And then we use the first law of reflection, which states that the angle of incidence is equal to the angle of reflection. So this is the angle of reflection, and it should also be 50 degrees. That means that this must also be 40 degrees. Just by following the same argument. So this ray will travel like this, come and strike the mirror at this point, and again get reflected. This ray happens to be the incident ray as far as the second mirror is concerned, but it is the reflected ray as far as the first mirror was concerned. So notice that a reflected ray can become an incident ray depending on whether it is leaving the mirror or approaching the mirror. That ray which bounces off the surface after reflection, it's called the reflected ray. The mirror which approaches the surface is called the incident ray. So, let's see, how much is this angle of incidence at this point? Notice that we do not know that angle, but we can determine it if we know this angle. Now, how do we know this angle? If we look at this shape here, it is a triangle. We've got to bear in mind that the total of the angles, the sum of the angles in a triangle, they add up to 180 degrees. That is why knowing this angle is important, so that when we add it onto this one, we get 160 degrees. We subtract 160 from 180, and we get this angle here to be 20 degrees. Again, remember this 20 degrees is not the angle of incidence. The angle of incidence is actually 70 degrees. How do I get that? I have to realize that the normal makes 90 degrees with the mirror, and therefore just by subtracting 20 degrees, I should be able to get this angle here, which happens to be the angle of incidence. And once I get the angle of incidence, I should know that this is the angle of reflection, which is what actually the question asks us to determine. The angle of reflection at the second mirror. Determine the angle of reflection on the second mirror. So one of the marks definitely goes here. When you identify that angle and indicate it on the diagram. It's not enough to calculate it elsewhere and say that the angle of reflection is this much if you have not indicated where that angle of reflection is found on the diagram, because this is also 70 degrees. But what is the examiner looking for? He's looking for the angle of reflection, this one here, on the second mirror, because there is also an angle of reflection on the first mirror. So read the question carefully. So what are the two concepts that are required in this kind of question? First of all, this question comes from a reflection of light at plane surfaces. And when you study reflection of light at plane surfaces, we come up with the two laws of reflection. Number one, it states that the angle of incidence is equal to the angle of reflection. Before you can state that law, you need to define the angle of incidence and the angle of reflection. For you to do that, you need to identify the two important rays in reflection. There is this ray which approaches the mirror, which comes towards the mirror before it bounces off the mirror. This ray which comes towards the mirror and strikes the mirror at this point, it's called the incident ray. The point where that incident ray strikes the mirror is referred to as the point of incidence. At the point of incidence, we usually draw a line, and in this question, this line has been drawn for you. It had already been drawn for you, so you don't have to struggle drawing it. This line, which is drawn at the point of incidence, is not a ray. It's drawn in such a way that it makes 90 degrees with the mirror. Here, this is 90 degrees, the whole of this angle. And that 90 degrees helped us to identify this angle here. I'm going to explain that angle in a minute. But remember, we've got the incident ray, which is the ray which approaches the mirror. The ray which bounces off the mirror is referred to as the reflected ray. At the point of incidence, we draw the normal. That normal helps us to identify the angle of incidence. The angle of incidence is the angle between the incident ray and the normal. The angle of incidence is the angle between the incident ray and the normal. This angle here. It follows that the angle of reflection is the angle between the reflected ray and the normal. That's where this 50 and this 50. That's why this is 50 degrees and this is 50 degrees, because we are using the first law of reflection. Don't get confused when they give you this angle here. This angle, many students think that this angle is the angle of incidence. It is not. It is simply an angle that the incident ray makes with the mirror. Remember, that is not the incident. It is not the angle of incident. The angle of incidence is the angle between the incident ray and the normal. The incident ray and the normal. That is the angle of incidence. While the angle of reflection is the angle between the reflected ray and the normal. The other thing is this. You've been asked to complete the ray diagram. This one here. It is important that when you complete this ray diagram, you show arrows. A ray diagram is never complete if arrows have not been included. So remember to show the arrows, because it shows the direction of travel of the ray or light energy. In which direction is it moving? Secondly, it helps you to identify the incident, the angle of incidence, and the angle of reflection, because you will have identified the ray which approaches the mirror and named it the incident ray, the ray which leaves the mirror and name it the reflected ray. You will find something striking here. When it comes to the second mirror, the reflected ray coming from the first mirror is now referred to as the incident ray. So by definition, the incident ray is that ray which approaches the mirror or comes towards the mirror. And then it gets reflected at a special point we call the point of incidence, where we draw the normal, and so forth. The second law of reflection states that the incident ray, the normal at the point of incidence, and remember the normal at the point of incidence is not a ray, so don't get carried away like some students do. They say something like this: the incident ray, the normal ray, and the reflected ray, all of them lie in the same plane. The moment you call the normal a ray, you've lost that point. So remember to state it like this: the incident ray, the normal at the point of incidence, and the reflected ray all lie in the same plane. That is how you state that. And those are the most important concepts as far as reflection at plane surfaces is concerned. And you can see how I've been able to use the first law of reflection to answer this question. Let's go to question 2. Now, in question 2, I'm going to explain why repulsion between two charged bodies is the only sure test of the sign that is carried by a certain body, is the only sure test that the body is charged. Let's use a question to study that. In question 2, we are told, state the reason why an increase in divergence is the only sure way of determining whether an object is negatively charged using a negatively charged electroscope. So, and this is the situation that we have. So first of all, let me explain about a neutral electroscope, because this is a neutral electroscope. A neutral body is one where the number of negatively charged particles, which are electrons, is equal to the number of positively charged particles, which are protons. So remember that even if we don't show the charges on a neutral body, it does not mean that it doesn't have charged particles. Charged particles are there, but the body is not charged. By a body being charged, we mean that one of those is in excess of the other. For example, a negatively charged body will have more electrons than protons. And we only show the excess electrons. A positively charged body, on the other hand, will have more protons than electrons. And in that case, we are going to show the excess protons. So this is a neutral electroscope. Remember, the number of electrons is equal to the number of protons, and we don't show it on the body. We only show it if the body has excess of either of those two charges. So a negatively charged electroscope means that it's got excess electrons, and that is why we show these excess electrons on the body. They are uniformly distributed in the whole body. So when they go down where we've got the rod and the leaf will be forced to diverge because there is a repulsion between like charges. That is the reason why the leaf diverges. Now, this electroscope can be charged by induction. So I'm just picking an electroscope that has already been charged, and it carries a negative charge. Now let's see when we bring a negatively charged body close to the cup. So over here, we have another object, maybe a plastic rod, that has been charged by being rubbed with woolen cloth. We know that when you take a plastic rod and rub it with a woolen material, it's going to acquire a negative charge. So again, I'm not concerned with how that body got charged. All I know is that it is negatively charged. When that negatively charged body is brought close to the cap of a negatively charged electroscope, what do you think is going to happen? There will be repulsion between the negative charge on the body and the negative charge on the electroscope. So that repulsion will cause some of the electrons to move down. Where we've got the leaf, there will be more concentration of negative charges on the leaf and on this part of the rod. That will create more repulsion. There was already repulsion here. Now that repulsion is going to increase, and therefore there will be more divergence. Why are we saying that this is the only sure test that the charge on the body is negative? Because that is what the question is asking us to explain. State the reason why an increase in the divergence is the only sure way of determining whether an object is negatively charged using a negatively charged electroscope. Let's look at the next slide and see what happens when we bring a positively charged body close to a negatively charged electroscope, and we also bring another body which is neutral. Let's see what happens. So this is what happens. This is a neutral body. You know, for the sake of understanding the interaction between the charges here and the charges here, I have shown the charges on the neutral body. Remember, a neutral body is one where the number of negatively charged particles, which are electrons, is equal to the number of positively charged particles, which are protons. And you can see they are the same. For every proton, there is an electron. For every proton, there is an electron. So this is a neutral body. We bring it from wherever it was close to the cap of a negatively charged electroscope. A negatively charged electroscope. Now this is what is going to happen. The negative charge on the electroscope is going to induce a positive charge on this side of the neutral body. What does that mean? It means that this negative charge on the electroscope is going to repel the electrons which are on the neutral body on this side, so that they move all the way to the other side. And I'm assuming that this negatively charged body is a conductor so that electrons can move, is a conductor of charge so that electrons can move. It's a material such as maybe copper, but it is charged. So once that repulsion happens, those electrons are going to move all the way to the farthest end of the neutral body, leaving the protons unpaired. Those unpaired protons are going to attract these electrons on the electroscope even more. So more of them are going to shift upwards. And when more of these electrons, which were evenly distributed, by the way, I left these negatively charged electroscope here so that you can be able to compare. So most of these electrons are going to shift upwards and concentrate here. If you look at the concentration of the electrons here, is less compared to the concentration of electrons here. Where have they come from? They've come from below here. So when they move, there will be less repulsion between the rod and the leaf collapses. But there is another object which produces the same effect. And this is when now we bring a positively charged body close to the cap of a negatively charged electroscope. That positive charge will have the same effect as the effect that we saw here. There will be attraction between the positive charge, and before I go to that, let me explain that when this negative charge on the electroscope forced the electrons on the neutral body to move to the farthest end, leaving this side positively charged. That is what we mean by the negative charge on the electroscope inducing a positive charge on this side of the neutral body. To induce is to bring into existence that positive charge here. So a negative charge will induce a positive charge in that body. If here we had a positive charge, then it will induce a negative charge. So let's go on. There will be attraction between the negative charge on the positive charge on the positively charged body and the negative charge on the electroscope. So again, more electrons are going to move up because they are being attracted by this positive charge. What will happen to the concentration of the negative charge on the leaf and the rod down there? It will reduce. Again, the leaf will collapse. So at this point, if we were trying to identify the type of charge on the body that we've just brought close here, we will not be able to do that, because whether the body is neutral or positively charged, it has the same effect. So here we cannot be able to tell the charge on this body. And the question is very clear. Why an increase in divergence is the only sure way of determining whether an object is negatively charged. So the only sure way we can be able to determine that the object is negatively charged, let me go back to the previous slide, is divergence, because it only has one observation. When you bring a negatively charged body close to a negatively charged electroscope, we are going to have an increase in divergence, which shows repulsion between the two like charges. And that is the explanation you can give to this. So you can put it in words that there will be repulsion between the negative charge on the body and the negative charge on the electroscope, leading to electrons moving down the electroscope, where they are going to cause an increase or the concentration of the negative charge, and this one will cause more forces of repulsion between the leaf and the rod, hence divergence. You do not need to explain about what happens when a neutral body is brought close or a positively charged body is brought close. What you have just said previously will be enough answer for that question. So go through the other concepts as far as charging the electroscope either positively or negatively by induction is concerned. Otherwise, we move to the next question, which is question 3. So let's look at question 3. In question 3, we are asked, figure 2 shows an incomplete circuit for an electromagnet. Complete the diagram to show how a battery should be connected to A so that the polarities of P and Q are south and north respectively. In part B, we are asked to state 2 ways in which the strength of the electromagnet in A can be increased. So there is a typing error here. I'm going to correct that. Now, this is an electromagnet. What is an electromagnet? It consists of a coil usually wound on a soft iron material. When we pass current through that coil, it makes that coil to be a magnet. Now, how do we determine the polarities of the magnet? We use the right hand grip rule. If this pen is the coil, I'm going to hold the coil in my right hand. the thumb will point in the direction of the North Pole, while the fingers will show the direction of the current in the coil. So when you look at point Q, we have been told that, point P, we've been told that at point P, there will be a South Pole. Let me just, yes, at point P, it's supposed to be a South Pole. That means that this part here will be a North Pole. So I'm going to hold that coil like this, with that part up there being the North Pole. And I can be able to see that according to my fingers, the way my fingers point, they point in this direction. Let me just see whether I can be able to ink this slide. Of course, I can be able to do that. So over here, since this side must be a North Pole, then according to the way I have held my hands, my fingers have pointed in this direction. I just needed to have one arrow on the diagram, just one arrow, and the rest of them follow. So it means that all these will be arrows pointing this way. It's a bit difficult to ink this particular diagram here, but I know current will flow like this in the conductor, which means that it's coming like this from the battery. That means this side of the battery must be the positive side, and the other side must be a negative side. So I draw maybe a battery of 2 cells, for instance, with this being positive and this being negative. That is how we find the polarity of the battery A. So this question was just about using the right hand grip rule. So on the diagram, you can go ahead and indicate the directions of the current, as I'm showing you here. And on the other side, definitely it will be like this. It's a bit challenging inking this particular slide, but you get the point. Should have used a different color to the color that I've used there for visibility, but hopefully you can see that the arrow in which direction it is pointing, making P to be south and Q to be the North Pole of that magnet. And do not confuse what we did in the previous question, which was on electrostatics, with what we are doing here, which is on magnetism. Many students confuse these two. For instance, when I'm marking these scripts, I usually get students who, when they are talking about magnetism, they start talking about the magnet being charged. You see, when you talk about charges, you're talking about electrostatics. And sometimes when you are talking about charges, they bring in the idea of South and North Pole. Don't get confused here. South and North Pole, these are poles of a magnet, and when we talk about magnetism, we talk about a material being magnetized, as opposed to when we talk about electrostatics, where we talk about a material being charged. So be careful when you're talking about these two. Part B, we are asked to state 2 ways in which the strength of the electromagnet in A can be increased. There are 2 ways we can do this. We can increase the number of turns in the coil, increase the number of turns in the coil, and number 2, increase the amount of current flowing through the coil. Let me point out 1 or 2 errors that students make when they talk about number of turns. Many of them talk about number of coils. That is wrong, because in this diagram, I only have 1 coil with several turns. The moment you start talking about increasing number of coils, you will definitely get it wrong. So get it first time that when we talk about increasing the strength of an electromagnet, we increase the number of turns, not the number of coils. Be careful at that point. The other one would be the simplest answer to give as far as the amount of current is concerned is just to say that increase the amount of current flowing through the coil. Don't go to tell us how that current is increased. If they wanted you to say that, they would have stated it here. State how the current in the coil can be increased. How? We can increase the EMF of the battery, or we can put a rheostat in series somewhere along that conductor and vary the resistance. That will also vary the current in the coil. So many of them state like increase the voltage or vary the voltage or something like that. It's always good to go direct to the point, because when you say increase the voltage, you are leaving it to the examiner you're leaving the examiner to fill out several blanks, and examiners are not supposed to do that. You're supposed to tell them what the answer is. Don't assume that they will know when you say increase the voltage or increase the EMF that will lead to the current increasing. There are so many other factors in that circuit which can cause the current to not increase even if the EMF has been increased. So never leave doubts in your answer. Never leave gaps for the examiner to fill in. That means in preparation for the exam, be very clear on the points. Strength of an electromagnet is varied when we vary the number of turns and we increase the amount of current flowing through the coil, and of course sometimes changing the shape of that coil so that we bring the poles close together. And the best kind of design is a U-shaped magnet. But they just asked us for two ways in which the strength of the electromagnet can be increased. This brings me to another point. If in an exam you've been asked to state two things, two factors, even if there could be three factors, just limit yourself to two, because this is what happens when you state more than one factor. The examiner will read the next factor. If the next factor is wrong, they mark it wrong and subtract one from the other two. You may have got the other two factors correct, but if you state the third one and it happens to be wrong, you lose a mark. Why should you lose that mark? You know why they subtract a mark? Is because they assume that when you are stating three factors, you are not sure of one of them. So you are stating them again for the examiner to choose the correct one. They are not supposed to do that. So if you're asked to state two things, just limit yourself to those two things. Don't be generous and give three or even four. Just state two, because by stating more than the number that is required, you are risking the marks which you already have. So that's what I can say about this topic. It comes from a topic in Form 2 magnetic effect of electric current. So again, go there and study more about magnetic effect of electric current. Otherwise, let's move to question 4. So let's look at question number 5. In question number 5, we are told that in a siren, sound is produced when a jet of air is directed perpendicular to a ring of holes on a rotating wheel. Explain the effect on the pitch of sound produced when the speed of rotation of the wheel is increased. Now, what is a siren? Over here in your course book, you've got this literature here. They've shown you the siren. It is actually, it consists of this disc. It's got a number of holes Some of them are far away from the center. Some of them, they are near the center. Some of them are wider. Others are very thin. And then there is a jet of air which is directed to these holes there. When this jet of air is interrupted, sound is produced. And you find that it is produced each and every time the jet of air is interrupted. It's more like when you get a test tube and you blow across the test tube. Sound is getting interrupted at the hole of the test tube. So the pitch of the sound produced by the siren is such that it varies with the speed of rotation of the disc, and at the same time it can also vary if the jet is moved towards the inside or towards the outside, because the speed of interruption of the jet of air varies. So we are asked, how will the pitch of the sound change if the speed of rotation is increased? So in the textbook we are told that a siren in form of a disc with a ring of equally spaced holes which are equidistant from the center is used in this case. When it is rotated at a constant rate and air blown through the holes as shown in figure 9.6, sound of a given note is heard. The disc may have concentric sets of holes about its axis to vary the frequency. The disc may have concentric set of holes about its axis. So you can see these are fewer number of holes, while on the outside we've got more holes. The speed with which the air is interrupted increases as you move towards the outside. So that is one of the ways in which you can vary the frequency. Another way in which you can vary the frequency is by changing the speed of rotation. And that is what this question is about. Sound is produced when a jet of air is directed perpendicular to a ring of holes on a rotating wheel. Explain the effect on the pitch of sound produced when the speed of rotation of the wheel is increased. So here we are varying the pitch not by moving the jet of air, but by changing the speed of rotation of the wheel. So this is what is going to happen. The holes interrupt the jet of air more frequently when the speed of rotation is increased. The sound produced will therefore have a high frequency, hence high pitch. In sound, the physical quantity which is represented by pitch is frequency. So you must mention frequency. The frequency at which the air jet is interrupted rises, and that means the pitch of the sound changes. And that's all about question number 5. Let's go to question number 6. So question number 6 is quite straightforward. It's about the defects of a simple cell, and we are asked, state the reason why the current produced by a simple cell falls rapidly when the cell is being used. A simple cell, so you should remember that this is due to the defects of a simple cell, which are local action and polarization. What is local action? Local action is that situation which occurs where the zinc plate reacts with the acid even when the cell is not connected to an external circuit. This happens because the zinc used is usually impure. So to reduce local action, we can either use a more pure form of zinc, or we can carry out a process we call amalgamation, where we coat the zinc with mercury. The other defect of a simple cell is polarization. What is polarization? Formation of hydrogen gas bubbles on the positive plate, which insulates the positive plate from the acid. But in this question, we were not asked to describe these defects. We were just supposed to say why the current falls. It's because of these defects of the simple cell. So just stating because of the defects of simple cell, which is polarization and local action, would be enough. And let's go to question number 7. So in question 7, this is about internal resistance of a cell. We are told that figure 3 shows a cell connected in series with an ammeter, a 2 ohm resistor, and a switch. A voltmeter is connected across the cell. When the switch is open, the voltmeter reads 1.5 volts. Now, notice that they are describing how we measure the EMF of a cell. First of all, we connect the voltmeter across the cell. Then we open the circuit. So when the switch is open, the reading of the voltmeter, by the way, it will not prevent the voltmeter from reading the potential across the cell. Okay? Because you can see that the circuit for the voltmeter is complete, although the cell is not sending any current to the external resistor. So here they are describing how you measure the EMF of the cell. So this reading of 1.5 volts is actually the EMF of the cell. Given that the internal resistance of the cell is 0.5 ohms, determine the current reading, determine the ammeter reading when the switch is closed. Let's see what happens here. So the EMF of the cell, this E, is 1.5 volts. The internal resistance, we can just write it here, is 0.5 ohms. This is the external resistor, uppercase R, lowercase r. So we are going to close the switch, and now current will flow in this circuit. This is I. Now this current is worked out like this. I is usually given by the EMF over the total resistance in the circuit, which is internal resistance, plus the external resistance. This will of course give me 1.5 volts divided by 0.5 plus 2.0. And this, if you calculate that, is going to give you 0.6 amperes. It's just as simple as that. So the trick here is to recall how you calculate current when you are dealing with a cell with a given internal resistance. The other trick they have used here is to describe how the EMF of the cell is measured. Remember, when the switch is open, the voltmeter reads the EMF of the cell. When the switch is closed, the EMF reads what we refer to as terminal potential. Terminal potential is always less than the EMF of the cell. However, they've not gone to terminal potential. They've just used two things. Do you realize when they are measuring the EMF of the cell? Do you know how the EMF of the cell is defined? They have described it here. When the switch is open, the voltmeter reads 1.5 volts. So the EMF of a cell is the reading of the voltmeter which is connected across the cell when the circuit is open. And the terminal potential is the reading of the voltmeter when the switch is closed. That is all to this particular question. Let's go to question 8. Question 8 is rather direct. You're asked to state two uses of gamma rays in medicine, and this one is very simple. Gamma rays are used to control and or to manage cancerous growth, or what we call malignant growth. The other use of gamma rays in medicine is in sterilization of medical equipment, that is to kill germs on maybe surgical equipment. So the two uses are as simple as that. Gamma rays are used in the treatment of cancerous body growth and in sterilization of medical equipment. Let's go to question 9. So in question number 9, this is about rectification. We are told that figure 4 shows the input and output signal on a CRO screen when two diodes are used during a full wave rectification. Explain how the two diodes rectify the input signal. So we are using two diodes. There are two types of rectifications. First of all, what is meant by rectification? Rectification simply means converting an alternating voltage into direct voltage, or an alternating current into a direct current, AC to DC. That is what we mean by rectification. In the rectification process, we usually use diodes. We could use 2 diodes, or we could use 4 diodes. The situation where we use 4 diodes is referred to as a bridge rectifier, but here we are restricted to using 2 diodes. So there is only one way we can do this. We need to use a center tapped transformer, and then the connection will look like this. This is how the connection looks like. So first of all, let's note that a center tapped transformer must be used. The 2 diodes are connected in such a way that each conducts a current through the load resistor during a particular half cycle. The circuit is of course shown in this figure. So this is it. This center tap, this line here, is connected to half the number of turns of the secondary. Half the number of turns. Let's see. When point A is positive with respect to point D, that means for this half cycle, all the way from here to here, if we draw a line here, we can assume that the voltage above that line are positive, while the ones below the line are negative. So when point A is positive with respect to point D, it means that current is flowing in this direction. You'll find that diode D1 is forward biased. It will conduct, but D2 is reversed biased. So this current, when it reaches this point, there is no way it can flow through this route because D2 is reversed biased. So it will take this route and flow through the resistor this way. Let me get the cursor. So it will flow. So remember, this is it. That one conducts. This one does not. So the current is going to flow through the resistor this way, and it will come this way, but it can't take any other route from there. It will have got to go back to A. So for that part of the cycle, this part of the cycle, the energy will have to be conducted through the resistor. In other words, current will flow. For the other half of the cycle, that is this particular half here, you find that first of all, with the red line here, A is positive and D is negative. That means D2 will not conduct while D1 conducts. Let me change here the color so that we can be able to understand what is happening here. So for the other half cycle, when D is positive and A is negative, find that D2 is going to conduct. But when that current reaches this point, it cannot flow through D1. So D1 will not conduct. So that current will take this route and it will flow through this resistor. And when it comes back to point C, it will move back to point D. So you can see that as far as the resistor is concerned, current is flowing through the same direction. Whether A is positive or negative, current simply flows downwards. You can see that current flows in one direction through the resistor. Whether the current changes direction or not, as far as the resistor is concerned, current flows through the same direction. And that is how we end up achieving full wave rectification using two diodes. So let me look at some further points here that I had written down. During the first half cycle, D1 is forward biased while D2 is reversed biased. I've already explained that. Hence the path taken by the current is A, D1, B, C, A. I've already explained that route. During the next half cycle, D2 is forward biased while D1 is reversed biased, and the path of the current is D, D2, B, C, D. Notice that during both half cycles, current flows through the resistor in the same direction. And that is how we would answer that question. I tend to feel that for you to be able to answer that part of the question, you actually needed to draw this particular circuit, because there is no way you could describe what is happening here without drawing. You must mention the center tapped transformer, So that's it. Let's look at question 10. In this question, we are asked, state how the intensity of X-rays in an X-ray tube can be increased. This is a very direct question. And we increase the intensity of X-rays by increasing the current which flows through the heater of the cathode. Or we increase the heater current. Don't just say increase the current. You've got to mention the current which flows through the heater. This one is different from increasing the strength of X-rays or the hardness of X-rays or the quality of X-rays. When we want to increase the hardness or the quality of X-rays, we are talking about the frequency of X-rays. When we want to increase the frequency of X-rays, we increase the accelerating potential. But here we are talking about intensity of X-rays. What does it mean by intensity of X-rays? By intensity, we mean increasing the number of X-ray photons which flow past a given point in the tube per unit time. This means that the number of electrons which are striking the metal target must also increase. For you to increase the number of electrons striking the metal target per unit time, then you've got to increase the rate at which they are produced. And you can only do that by increasing the heater current. So the answer here is quite direct. It's just by increasing the heater current. Let's look at question 11. In question 11, we are told that figure 5 shows part of the lighting circuit in-house. State 2 errors in the wiring of the circuit. First of all, when we study this, we find that we must bear in mind that the lamps in domestic wiring must be connected in parallel to each other so that each one of them works normally. That is how we connect lamps in the house. Then there is the switch and there is the fuse. The switch must be connected to the positive, or to the switch must be connected to the live wire. And so is the fuse. Is this the case in this connection? Let's check. When we follow the live wire like this, we get to the lamp, and then it is after the wire comes from the lamp as it goes to the neutral that we have the switch connected. So we can directly see that for lamp A, the switch is not connected correctly. It's not connected correctly. It's connected to the neutral instead of it being connected to the live wire. So that one is an error. Is it the case with the switch in lamp B? I think the switch in lamp B, I can see that this line is connected to the live wire. So I can't say anything, whether there is anything wrong here. There is nothing wrong here. Let's look at the fuse. The fuse, for both of them, instead of being connected to the live, it's connected to the neutral. So you can see that is the second error. The other error is that when you look at lamp B, both the wires of the lamp B are connected to a point which is at the same potential, 240 volts each one of them. There is no potential difference across the lamp. So this lamp will not work. So because the two wires which go to the lamp are connected to the live wire. So those are the two, or they are the three errors actually. But remember, it's only two that were required. So number one, the fuse is connected to the neutral wire instead of the live wire. Number two, the switch for lamp A is connected to the neutral wire instead of the live wire. And number three, lamp B will not light since both of its terminals are connected to the live wire. They are connected to the same potential, making the potential difference across the lamp to be 0, and therefore there will be no current flowing through the lamp, because there must be a potential difference across the component for it to work. Now I've redrawn this circuit with the connections done correctly, and this is how it looks like. You can see I've shifted the fuse from where it was on the neutral to the live. That's the first thing I've made. And then I've shifted the switch, which was for lamp A, the switch was connected to the neutral. I've shifted it to the neutral, to the live wire. And of course, I've reconnected this circuit here correctly with the switch now on the live, and the other wire, instead of being connected to the live, it's connected to the neutral. So this way, both lamps are connected correctly with the fuses and the switches connected correctly. And let's look at question 12. Now this is question 12, where we are told that uranium decays as shown below. Uranium-234 decays to give thorium-230, and we are supposed to name the particle which is emitted during this decay. Let's see what happens. The atomic number of this particle should be A, while the proton number over here, we can give it, let it just be P. Let it just be P. When we look at the masses, we are supposed to say that 234 is equal to 230 plus A. And this, you can see that A must be equal to 4. So the radiation which is emitted has mass 4, atomic mass 4. How about the proton number? The proton number again is 92 is equal to 90 plus P, and this implies that P is 2. And you find that this particle is actually an alpha particle. So here you're just going to say either it is, you can write it like this, 4 He 2, and then you put 2 positive. Anyone looking at it will understand that this one is a helium nucleus, or you can just write this one here, helium nucleus. Another person would just say that it is an alpha particle. Alpha particle. Or you can just say it's just alpha. That is a symbol for the alpha particle. So, or any one of these is acceptable. You just need to state one of them. And let's look at question 13. In question 13, we are asked to state the disadvantage of using a convex mirror as a driving mirror. What is the disadvantage here? First of all, let's look at the advantage. The convex mirror gives the driver a wide angle of view, so the driver is able to see a lot of details behind his or her car, because the driving mirror is meant to allow the driver to see behind the vehicle that the driver is driving, so to speak. So if it can give as much information behind the driver as possible, the better it is. So it's got a large angle of view, and that one is an advantage. The disadvantage comes in when the driver looks at the driving mirror. The image of the cars behind, or the objects behind, they are diminished. They are very small. This gives the driver a false impression or judgment about distance behind his vehicle or her vehicle. We find that the driver thinks that the vehicle behind is very far, or gets the impression that the vehicle behind is very far, while the vehicle could be very near, and that can possibly cause an accident. So we can say that the disadvantage here is that the convex mirror gives the driver a false impression of distance. So let's see. It forms a diminished image of the cars or objects behind, giving a false impression that they are very far while they are actually near the car. So that is a disadvantage. And let's look at question 14. So let's look at question 14. This is the last question in section A. You realize that questions in section A just require short answers, simple calculations, simple explanations, and so forth. And this is one of them. We are told that figure 6 shows the radiation from the sun passing through glass in a greenhouse onto the floor. The floor emits radiation. State the name of the radiation emitted by the floor. This is, of course, infrared. Infrared is the radiation which is emitted by the floor, and that radiation is trapped by the glass, and it warms up the inside of the greenhouse. It's just as simple as that. So let's look at section B, and we start with the question 15, which has got 11 marks. And we start with the A, where we are told on the axis provided, sketch a graph of capacitance against the area of overlap of the plates on a parallel plate capacitor. And here we would like to remember that the capacitance of a capacitor, I would like to remember that the capacitance of a parallel plate capacitor is given by permittivity of free space, epsilon naught, area of overlap, divided by the separation between the plates. So you can see that the capacitance is directly proportional to the area and inversely proportional to the distance. We've been asked to state how the capacitance depends on area of overlap and definitely it will be a straight line through the origin, because a straight line through the origin shows that the physical quantity on the y-axis is directly proportional to this one here, the one on the x-axis. So that one was just as simple as that. Part 2, we are asked to draw a circuit diagram that may be used to investigate the discharge process of a capacitor. Now, the process of discharging a capacitor cannot be isolated from the process of charging it. So, I've shown both circuits whereby when this toggle switch is on this side, then it enables us to record the current and the voltage during the charging process. And when it is fully charged, the voltage will remain constant, or the reading here will remain constant, and this one will show 0. So this one will be a maximum, this one will show 0. That is when it is fully charged. Now to discharge it, I'm going to move this toggle switch to the other side. So this circuit here that I've drawn in green is the one which was expected. But like I've put it, we cannot divorce the charging process from the discharge process, because the moment you touch a charged capacitor, it immediately discharges. So it's just important to connect or to investigate the charging and the discharge simultaneously. So the moment we connect this toggle switch on this other side, the capacitor starts discharging across the resistor. So there must be a resistor here for us to be able to observe how the voltage changes with time, and again how the current changes with time. That resistor is important. So that is the kind of circuit that we would expect. And then we are expected to draw on the axis provided, sketch the graph of potential difference between the plates against the time for the discharging process. Of course, it's going to be exponential. The voltage is going to decay out like that. That's what was expected. Now let's look at part C, where we are given this network of capacitors, and we are expected to determine the effective capacitance in the circuit. So the first thing we notice that this one is a series parallel connection of capacitors. When you are given this, we usually identify the kind of capacitors which we can easily combine. In this case, it is this capacitor and this capacitance. And remember, when capacitors are in parallel, we simply add their capacitance. For example, I can combine this and this to get a capacitance of 5 microfarads. And then now I've got two capacitors which are in series. At this point, because it's just two capacitors which are in series, I simply need to get the total capacitance, CT, will be equal to the product of the two, which is 4 times 5, which gives me 20, divided by the sum, which is 9. And this will be 2 and 2 over 9, or 2.22 microfarads. That is what I get here as the total capacitance, or the effective capacitance. Now I can use that total capacitance to calculate the total charge which is stored. So Q is equals to CV. If it is total charge I want, I must get the total capacitance, which I know, times the total voltage from the battery. And that one is very easy to get, because let me just do it here. The total capacitance is 9 over 20. Let me just use 20 over 9 microfarads times 6 volts. I can convert this into farads, in which case I'm going to get this one in coulombs, but I can leave it in terms of microfarads in which case now I'm going to get my answer in terms of microcoulombs. So I prefer to do this. Divide by 3, I get 3. Divide by 3, I get 2. And that is going to give me 40 over 3. This one will go in here 1 because of 3. And then 3 goes into 10. 3 times. And a third, or 13.33 recurring microcoulombs. So that is the total charge stored in the circuit. Now you'll realize that this total charge is the same charge which is stored across the 4 microfarad capacitor. Same charge. But when it comes here, the charge is split. Simply because current splits, then charge is going to be split. But this one, because it is in series with this one here, the charge stored here is equal to the charge stored in the 5 microfarad capacitor. While the charge stored in the 5 microfarad capacitor is the sum of the charge stored in the 2 microfarad capacitor and the 3 microfarad capacitor. So over here, since I want now the voltage, I'm in part 3 now. I want the voltage stored, or the potential difference across the 4 microfarad capacitor. When I use this equation, V is going to be equal to charge over C. The charge stored there is 13.3 microcoulombs. Divide by the capacitance, which is 4 microfarads. Let me see what that gives me. That will be 13.3. We divide by 4, and we find it is 3.325 volts. 3.325 volts. That will be the voltage across the 4 microfarad capacitor. The rest of it is dropped across the 5 microfarad capacitor. And you can see that the larger the capacitance, the smaller will be the voltage. So the PD across the 5 microfarad capacitor, which is a combination of these two, is definitely going to be less than half of this value. But of course, very close to it. And that is how you would work out question 15. Let's go to question 16. Okay, let's look at question 16. In question 16, it is on waves and properties of waves. And they start by asking us to define these characteristics of waves, amplitude and wavelength, each for 1 mark. You'll remember that amplitude is the maximum displacement of the particles of the medium from equilibrium position on either side of the equilibrium position. You could also describe it as the maximum displacement of a wave disturbance, because it's not all waves which have got particles. Think about light. Although we do talk about photons as being synonymous with light, with particles in light, when we look at particulate nature of light, it's not. At the beginning, we realize that we cannot talk about particles in light at the very, very beginning. That is why you can also be given a mark if you say it is the maximum displacement of the disturbance from equilibrium position. But let's stick to the standard definition. The maximum displacement on either side of the equilibrium position of the particles of the medium from equilibrium position. Wavelength. Wavelength is the distance between two particles in a wave which are following each other. That is, they are consecutive and they are in phase. I'm going to explain those terms in a moment. But first of all, let's look at these definitions. Maximum displacement of the particle of the medium from equilibrium position. That is the definition of amplitude. When it comes to wavelength, it is the distance between any two particles which are consecutive and they are in phase. Now, when you look at this wave here, this could be a displacement distance graph. This crest and this crest, they are following each other. Therefore, they are consecutive. Points which are consecutive are following each other. And the distance which separates them will be the wavelength. Sometimes you can even define the wavelength as the distance between two consecutive crests, or the distance between two consecutive troughs, or if you want to get the standard definition, or to use the standard definition, distance between any two particles which are consecutive and in phase. I've explained the meaning of consecutive points. Remember, they are following each other. Remember, this one is a crest and this one is a crest. This point on this crest and this point on this crest, they are in phase, but they are not consecutive. So the distance between them will not represent the wavelength. It will represent two wavelengths. But we want the definition of one wavelength. That is why you must mention there the idea of being consecutive. How about being in phase? Points on a wave are said to be in phase if they've got the same displacement from equilibrium position and are moving in the same direction. I'm going to use a simulation to show you this. So let's go to the simulation. So first of all, I want to look at waves. So first of all, I want us to look at waves on a string. If you're holding one end of the string and your friend is holding the other end, and then you move the string or the rope up and down, then this is what you're going to see. So you can see that, just take this point here, the green particle here, to be your hand. You're moving your hand up and down. Or better still, let us think about something like this. There is this rope and we want to move this side of the rope up and down. Up and down. You can see that is what you end up having. But I want it to oscillate smoothly. I want to get smooth oscillations. So let's look at the maximum displacement of the particle from equilibrium position. This dotted line here represents equilibrium position. And you can see the green particle, it has already moved a certain amount of displacement. This particle here, the green one, has moved this maximum displacement. That is the amplitude. Notice that before it gets to the maximum displacement, it's got all sorts of displacements. It's got this positive displacement, this one, it is increasing until it has maximum displacement. And then that displacement starts reducing, it becomes zero, and then it starts moving in the opposite direction, which is negative displacement, until again it achieves a maximum displacement in the negative direction. So we have already looked at amplitude as the maximum displacement of the particle from equilibrium position, maximum displacement. Now let's look at wavelength. Let's choose points which have got the same displacement and they are moving in the same direction. So let me get this rule here. I'm going to put it here, and let's see, we identify this point as being on its way upwards, I think it's on its way downwards. This point here, it's on its way downwards. It's got a certain amount of displacement which we can measure here and find that it is approximately, this is 1 centimeter, this is 0.6. Let me use this. Let me just try to use accurate values. Yes. So since this one is 1 centimeter, the displacement of this particle is 0.6 centimeters positive. Let's look at other points with the same amount of displacement. This particle here approximately has got the same displacement as this one here, but this is moving upwards while this is moving down, so they are not in phase. Let me look at another particle which has got the same displacement. It is this particle here. It's got a displacement of 0.6 centimeters and it is moving upwards. So definitely this one and this one, they are in phase because they have fulfilled the conditions for particles in a wave to be in phase. Particles on a wave are said to be in phase if they are moving in the same direction and they've got the same displacement from equilibrium position. So the distance which separates those 2 points which are in phase and they are consecutive, then it forms the wavelength. This green particle here has got maximum displacement which happens to be about almost like 0.9 centimeters. The other particle that has got the same displacement is this one here, maximum displacement. And you can see this one is on its way downwards and this one is on its way downwards. So they are in phase. They are moving in the same direction. They are moving in the same direction. They've got the same displacement, which is maximum displacement, and they are consecutive. Therefore, the distance which separates them is the wavelength. So remember that. Wavelength is the distance between 2 particles in a wave which are consecutive and they are in phase. That is complete definition of wavelength. So let me now go to a different system that can also be used to study this. Over here, I've got a simple pendulum. I can be able to displace it through a certain amount of degrees. Let's say that is 10, 20. I think that is, it's 20 degrees. And I can set it in oscillation. So this maximum displacement of the particle, this is the particle of the medium. This maximum displacement of the particle from equilibrium position is what I would regard as the amplitude. This time it's negative, and when it's moving in this direction, it is positive. Now let me use the simple pendulum to also show you particles which are out of phase. First of all, let me show you the ones which are in phase. I've deliberately made the displacements, the angular displacement of these 2 particles to be a bit different. But because the periodic time depends on the length of this string, provided this angle is small enough, then they will have the same period. So these 2 particles are in phase. They are oscillating in phase. They always are in phase. So how about particles which are out of phase? That will be these particles here. These particles are 180 degrees out of phase. I'm going to use that when we come to, I think, part C of that question, where we look at constructive and destructive interference. Hopefully you are getting this idea of particles being in phase, particles being out of phase, the idea of amplitude, the idea of wavelength. Now let's go back to the question and see the rest of the questions. So we have already looked at the definition. Let's look at the other questions. This question is about the reflection of waves. You can see we've got a straight barrier and circular waves. This is the source of the circular waves. These are wave fronts. They actually represent crests. In between one crest and the next, we've got a trough. And we've been able to see this from the previous wave, where we've got a trough. It happens to be in between two crests. So understand that. So let's look at the question. Figure 8 shows water waves approaching straight reflect at a speed of 40 centimeters per second. We are asked to draw in the diagram the reflected waves. Now, the first part of this wave front to be reflected is this one. So it will bounce back while this one is still on its way to the barrier. So by the time this particle gets to the barrier, this one simultaneously gets to the barrier, because you can see the direction of travel of this wave is like this. So this, by the time this one gets here, this one simultaneously gets there. And this one will have been reflected. It will have bounced back. So if we get the first wavefront, reflected wavefront, we can draw the others. So let's see what we have. That is what we have. So this wavefront, like you can see, it reached here and it got reflected that way. It reached here and got reflected this way. Now, I'd like you to observe this. This one is an incident ray. It travels like this. It strikes the mirror and it's along the normal. So it gets reflected along the normal. So this part of this wave, when it strikes the barrier, it gets reflected right back. But this part of the wavefront, you can see that is the incident ray. The reflected ray will be in that direction. And that is why these waves, they start moving in this direction. So the reflected waves will be moving that way, and even on this other side, they'll moving this way. But I've got the first wave front, the first reflected wave front. All I need to do is now identify the direction in which that wave is traveling, trace it backwards, come here, get the same direction in which it is traveling. And how do I do that, by the way? I have to remember that this is the incident ray. When it gets at this point, I realize that this is the point of incidence. I can draw a normal there and be able to determine the angle of incidence as well as the angle of reflection using the laws of reflection. That is how I get this ray here. If I extrapolate this line backwards and I do the same to this line backwards, they meet here. But the reflected waves are traveling that way. So they appear as if they are coming from this point. They are circular waves and they appear to be coming from this particular point here. Another way in which I can be able to identify this point is to say, this is the object. This is the object distance. I come behind the mirror in quotes, and I get the same distance and I identify where the image is supposed to be. Once I get that point, it's just a matter of now drawing these directions of the reflected waves as they move outwards like that. Now, another thing that I'd like you to observe closely is that during reflection, it's only the direction of travel of the wave that changes. Nothing happens to the speed of the wave, nothing happens to the frequency, nothing happens to the wavelength. So remember that this is a crest and this is a crest as far as this dark wave is concerned, the black one is concerned. This is a crest, this is a crest, so this must be the wavelength. So I maintain the same wavelength. So don't get carried away and just start drawing curved waves and you don't observe the wavelength. So part of these 3 marks, they go into checking those aspects. The shape of the wave, have you maintained the wavelength to be the same? Have you shown the direction in which the reflected wave is traveling? Because the reflected waves, they are traveling this way, this way, this way, and this way. Could even draw arrows here. Could continue with this arrow, continue it this way, continue it with this way, come here, draw another one which points right in the opposite direction, come to the middle. Of course, you're using this as the reference point. Draw another one like that and continue with it that way. The waves behind the reflector must be dotted because they are not real. These are the ones which are real. And that is how you would answer that part. Now let's look at a situation where we've been asked to calculate the wavelength of the waves. Remember, we've told that given that the distance between the source and the reflector is 15 centimeters, so this is the source and this is the reflector, and we are told that this is 15 centimeters. We need to realize that where the source is, you can regard that to be a crest. This is a crest. So there is a wavelength. So remember that the source is here, and where the source is, it's a crest. 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths. They occupy a distance of 15 centimeters. So in order to get 1 wavelength, we will divide that 15 centimeters by 4. 1, 2, 3, 4. And let's do exactly that. So to get part 2 here, we are going to find that the wavelength will be 15 centimeters. That one we are going to divide by 4. Let me just quickly do that. That is 15. We divide by 4 and we get 3.75 centimeters. That is the wavelength. Part 2, the frequency of the waves. Now, I realize that for me to get a frequency, I just need to divide the speed by the wavelength. How much is the speed? I had been told that it is 40 centimeters per second. I divide that one by 3.75 centimeters. Let me see what I get. So I have 40. I divide by the answer that I've just got previously, and I get 10.67. And decide that the unit is per second, which is the same as hertz. 1 per second, the same as 1 hertz. That is how I get the frequency of the waves. And it's just as simple as that. Let's go to part C. So in part C, this is about interference of waves. And we are told figure 9 shows light rays from 2 coherent sources, S1 and S2. What are coherent sources? Coherent sources are 2 sources of waves, in this case light, which have got a constant phase difference. The phase difference does not change. They've got a constant phase difference. If they start by being in phase, they remain in phase throughout. So they've got a constant phase difference. Remember that. Dark and bright fringes are observed between A and B. State how dark fringes are formed and how bright fringes are formed, how dark fringes are formed, and then state what is observed when light of a higher frequency is used. I will take this point to take you through interference using Young's double slit experiment. Now this one is a double slit. Normally we would have a source of light here, just a single source. Then we'll have a single slit which is going to diffract the waves. Diffraction is a spreading of a wave when the wave moves through a small gap or around small objects. That is diffraction. So we would have a source of light, and the light we would use is monochromatic, light of one frequency and consequently one wavelength. Monochromatic, or light of one color. So we are going to have, we can have white light here, and then we have a filter, let's say a green filter, so that it just allows green to pass through and then cuts out all the other colors. So what we have there after the lamp is just light of one frequency or one color, which is green. Then after that, we are going to have a single slit, which is going to diffract the waves. And then after that, we're going to have a double slit. Notice that the two sources here, they're also going to diffract the waves. Each one of them will diffract the waves. We are going to have circular waves here, circular waves, and then the two are going to interfere. The reason why we use one source of light and then split it into two so that it appears as if it's two sources is to ensure that the two sources of light are coherent. Remember what we mean by coherent. By coherence, we mean that the two sources have got a constant phase difference. For us to achieve that in light, the best way is to get the two sources from one single source. And that is the main reason why the headlamps of a car do not form an interference pattern, because the two headlamps are not coherent sources of light. So let's get ahead. So the wave trains from this source and this source are going to interfere. They are going to meet at this particular region here and form an interference pattern. And that is what I've drawn here. Just want to show you as a simple interference pattern. Actually, what happens, I want you to concentrate on this source one here and this first green wave, which is traveling like that. And it reaches this point. And then I want you to come to the source number 2 and follow the red one until it gets to that point. By the time they reach here, they are in phase. They are in phase. Notice that they started by being in phase. This one is moving up, and this one is also moving up. They are in phase. And when they end up there, they are in phase. We are going to get constructive interference. Constructive interference happens when two sources of light meet at a point and they are in phase, so that wherever a crest meets a crest, a bigger crest is formed, or wherever a trough meets a trough, a bigger trough is formed. This is what I'm talking about. Constructive interference happens this way. A crest due to one wave meets another crest due to the other one, and a bigger crest is formed. That is, if this is amplitude A, this one will have twice the amplitude. Or if we have a trough, it meets another trough, it's going to form a bigger trough. This is constructive interference. So when they are asking us how bright fringes are formed in terms of light, when light interferes constructively, it forms a brighter region, a brighter fringe. Why is it brighter? It's because its amplitude has increased. The intensity of light at that point has increased, so it appears much, much brighter. However, there are some other points between two constructive interference where we've got destructive interference, where there is a crest meeting a trough and the two destroy each other. The two waves which meet at this point, because this point is a point where we've got destructive interference. You can see they are out of phase. One particle, they are exactly 180 degrees out of phase. When one particle is moving down, the other one is moving up. And therefore, they end up destroying each other. So, destructive interference happens when a crest meets a trough, and this is what happens. While constructive interference happens when a crest meets a crest or a trough meets another trough to form a bigger crest and a bigger trough respectively. But let's look at the actual condition that must be fulfilled for us to have constructive interference. If you count the number of wavelengths you have here, 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half. We've got 9 and a half wavelengths. Let's look for at the red one. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and a half. For the red one, we've got 10 and a half wavelengths. When we look at the path difference, the path difference is 10 and a half minus 9 and a half, and we get 1 wavelength. The condition for constructive interference to be formed is that the path difference between the wave trains from source 1 and source 2, path difference, should be equal to n lambda, should be equal to a whole number multiple of the wavelengths, where n could be 0, 1, 2. They're just natural numbers, and so forth. When the path difference is 0, we've got the central bright fringe here. The path difference, this green wave here, when they meet at this point with the red one from this point, this one has traveled exactly the same distance as this one. Therefore, the path difference is 0. Constructive interference. And again, you can see when they meet at that point, they are in phase. Constructive interference is taking place. So that is the condition for constructive interference to take place. Destructive interference, at this point, if we were able to count the wave, the path difference here compared to the path difference here, we will find that it is exactly equal to half a wavelength. Half a wavelength. And we can be able to do that. So for destructive interference, this one applies to this situation. For destructive interference, the condition that must be fulfilled must be n plus a half lambda. So that, again, n takes these numbers here. When n is 0, you're going to get the path difference to be half a wavelength. So we're going to find a crest is meeting a trough because the two are separated by a half a wavelength. A crest and a trough, they are separated by half a wavelength. So that is the condition for destructive interference and the condition for constructive interference. Let's look at the final part, which asks us this. State what is observed when light of a higher frequency is used. Now, the distance between one fringe and the next, which is called the fringe separation, this one here, this distance here is called the fringe separation. We're going to call it x. The distance from the double slit all the way to the screen is given the symbol d. The separation of the two slits is given the symbol A. The fringe separation X is related to all these factors by this expression, going to be equal to lambda d over A. Lambda is the wavelength of the waves. Remember, these waves are monochromatic. We said we are going to use green. They are monochromatic. It also depends on the distance of separation between the double slit and the screen. It also depends on the slit separation. A is the distance between this slit and this slit. So you can see that from here, and let's remember that lambda is equals to speed over frequency. So instead of lambda, I can have speed over frequency times d over A. What I want to show you here is that X is inversely proportional to the frequency. What that means is if frequency increases, X is going to reduce. And here we are talking about what is observed when light of a higher frequency is used. The value of X is going to reduce. The fringe separation is going to reduce. And you can explain that using this. Although we have seen that X is directly proportional to the wavelength, if frequency increases, the wavelength is going to reduce. If wavelength reduces, then X is going to reduce. So you can trace it back using frequency, which is directly related to X. Or you can use this relationship direct. And that is how you would answer question 16. Let's move over to question 17. Okay, here we are in question 17. Question 17 is on a refraction of light. And what are we given here? We are told that figure 10 shows a ray of light traveling from glass to air, determining the critical angle of the glass-air interface. Critical angle. What is critical angle? And when do we talk about critical angle? We talk about critical angle when the ray is moving from an optically denser medium into an optically less dense medium. For example, in this case, you can see that the ray is moving from glass, which is optically denser compared to air. So it's moving from a material with a higher optical density to a material with lower optical density. So you expect the angle of refraction in air to be greater than the angle of incidence in glass. And remember, the angle of incidence is the angle between the normal and the incident ray. And you can see over here that that angle is 42 degrees. This is this angle that we are talking about. The angle of refraction is found in air, and it is the angle between the normal and the refracted ray. And this is the refracted ray. The next thing is this. You realize that the angle of refraction in air is 90 degrees. It is at that point that we realize that actually 42 degrees is the critical angle. Critical angle is the angle of incidence. The angle of incidence in the optically denser medium, for which the angle of refraction in the optically less dense medium is 90 degrees. And you can see those conditions have been fulfilled. And that is how you identify 42 degrees as the critical angle. So you'll just say here that the critical angle C is 42 degrees. And it is just as simple as that. There was no calculations involved. Then we are asked to calculate the refractive index of glass. So we remember that we can be able to calculate the refractive index of that optically denser medium if we know the critical angle. So that's it. Critical refractive index of glass is 1 over sine C, where C is the critical angle of that particular medium. So we're going to say this one is 1 over sine of 42 degrees. Let's see what that gives us. 1 divided by sine of 42, and I get 1.49447. We could say it is approximately 1.5. 1.5. And that is how you work out that part. Let's look at part 2. We are given that a piece of metal is embedded at the center of an ice block 14 centimeters from the surface of the ice. So there is this ice block here. There's the ice block. There's the surface of the ice block. And we have this piece of metal inside here. Inside there. We are told that it is embedded at 15 centimeters from the surface of the ice. So this is how far it is. 15 centimeters. What else are we given? Given that the refractive index of ice is 1.32, determine how far from the surface of the ice the metal appears to be. So if we were to look at that material from above here, where will it appear to be? It will appear to be near us. It will appear to be somewhere around here. So how much will that depth be? How far will it be from the surface? Now here we are talking about the real and apparent depth. This is the real depth. 15 centimeters is the actual depth of that metal from the surface of this material, while the apparent depth is how far it appears to be. The refractive index of this material, N, is given by the real depth, depth over the apparent depth. So here we have got the apparent depth. The apparent depth is the depth that the object appears to be, how far it appears to be from the surface. So the real is 15, while the apparent is D, but the refractive index is 1.32. And we see that the apparent depth is 15 divided by 1.32. What does that give us? So we get 15 divided by 1.32, and I get 11.36 centimeters. You can say 11.4 centimeters approximately. So observe how they have described real depth and the apparent depth, because that skill is required. And then how you identify that you've got to use this concept of real depth over the apparent depth to determine the refractive index of the material. So let's go on to the next question. This is about refraction. It's about lenses, and lenses work on a refraction of light. Over here we've got a diverging lens. Figure 11 shows two rays of incidence on a diverging lens. Complete the ray diagram to show the path of the rays after passing through the lens. Number one, you observe that these two rays are parallel to each other, and you observe that one of them is passing through the optical center of that particular lens. The optical center of that particular lens. What is it that we expect? If you put your ruler against on this line like this, you will also observe that this ray passes through this F. In the actual question paper, you find that they had made these distances different. So this was a little bit shorter than this one here, the focal length. That one is possible because the curvature of the two surfaces of the lens need not be the same. But at this level, we usually study lenses which are of uniform shape. That is, if we are talking about a diverging lens, for example, the focal length on one side should be equal to the focal length on the other side. So I don't know whether that was intentional or, by mistake. So I just drew this diagram, making the two focal lengths to be the same. And when I looked at that diagram properly, I found that this ray actually passes through F. A ray, actually, it appears to pass through F. It actually does not pass through F. If it was a convex lens, it would appear to pass through. It would pass through F. But for a diverging lens, it appears to pass through F. So what would happen to this ray? First of all, let's agree that this one will pass on undeviated. It will not bend at all. It will just pass on straight. But this one, since it appears to pass through F, it will be refracted parallel to the principal axis. And using this refracted ray and this refracted ray, I would extrapolate this one backwards and see that they met somewhere around here. And this is the diagram that I got. So this one, because it appears to pass through here, then it would be refracted parallel to the axis. When I extrapolate it backwards like this, then they meet somewhere around here. And this would be the focal plane. Now, the fact that these two rays are parallel to each other means that they would appear to meet at the focal plane. The focal plane. So, and if you draw this diagram accurately, you'll find that wherever they appear to meet will be somewhere along this vertical line here, which identifies the focal plane of this lens. How about if that lens was somewhere else, but still parallel to this? What would happen? So I also included a ray here, which is parallel to these two, just to show that it will be refracted in such a way that they meet at the focal plane. So remember, this ray need not necessarily pass through this F, but provided it is parallel to the one which passes through the center here, the two are parallel, they are going to diverge. And they will diverge as if they appear to come from the focal plane. Focal plane. The only point they would appear to meet at the principal focus is if they were parallel and the two rays are parallel and they are also parallel to the axis. That is when they will appear to meet somewhere here. So I thought of adding this green ray here so that I can show you what would happen if situations change. And let's go to part D, where we are asked to state two differences between the human eye and a camera. We are also asked to name the part of the eye that enables the lens to focus images of the objects at different distances. First of all, let's look at the human eye and the camera. They are quite comparable. So we are asked to compare the differences between the human eye and the camera lens, this lens and this lens. Of course, both of them are convex. All those are similarities. Let's look at the differences. What would be the differences between them? The differences are as follows. The focal length of the eye lens is variable, while the focal length of the camera lens is fixed. Now, how is that possible, to vary the focal length of the human convex lens? We make use of the ciliary muscles, which when they contract, they make the lens thick and therefore reduce the focal length. That is when they relax. When they contract, they make the lens to be thin and the focal length increases. Number two, the camera with zoom lenses has variable image distance. You are able to vary the image distance, especially when it has got a zoom lens, while the eye has a constant image distance. You're not able to vary the image distance in the eye. I've given a third difference. Only one photograph can be taken at a time when the shutter opens, but the eye is always open to form constant changing pictures. So those are some of the differences that you would be able to quote. Only two were required. So I've given you three so that you can be able to understand the third one. And of course, the name of the part of the eye that enables the lens to focus images of the objects at different distances is, of course, the ciliary muscles. The ciliary muscles. If we go back there, you'll be able to see the ciliary muscles. These are the ciliary muscles. When they contract, they make the lens to be thin, and that is going to vary the focal length of the lens. When they relax, they make it thick, and it's going to shorten the focal length. So that is it about question 17. Let's move over to question 18. Now, in question 18, we are asked to describe how a magnet can be demagnetized using the electrical method, demagnetization. At this point, you know that obviously we use alternating current. We must use a coil, pass alternating current in that coil. First of all, put the coil facing in the east-west direction. Then put the bar magnet inside the coil. Of course, now it will be facing in the east-west direction. Pass alternating current through the coil for some time, and then remove the magnet slowly from the coil, and it will have been demagnetized. How do we test whether it has been demagnetized or not? We simply need to suspend it, and if it has been demagnetized, it will point in any direction when it comes to rest. But if it has not been demagnetized, it will point in the north-south direction of the earth. So these are the points that you need. A 12-volt AC voltage is connected in series with a solenoid, which is placed with its axis pointing east-west. So you need not state the actual value of the voltage that you connect there. Just mention that you connect alternating voltage to the coil, and the coil is pointing in the east-west direction. The bar magnet is to be demagnetized is placed inside the solenoid, and the alternating current switched on. After a few minutes, it is withdrawn slowly from the solenoid, and when suspended freely, it does not settle in any particular direction. This shows that it has lost its magnetism. And this is a diagram that shows that, because sometimes we are asked to illustrate or to explain using a diagram. So I've included a diagram there that you can be able to study and see how you can replicate the same. Let's look at part B. In part B, you are provided with the two iron bars, P and Q. One of the bars is magnetized while the other is not. Explain how the magnetized bar can be identified without using a magnet or a magnetic material. So they have prevented us using repulsion as the only sure test of polarity or magnetism. What is it that we are expected to do? It's very simple. Just suspend each one of those bars, iron bars, using a cotton thread, one at a time, and using wooden stands. The one which is a magnet, and ensure that they are free to rotate in a horizontal plane. The one which is a magnet will come to rest pointing in the north-south direction. The other, which is not a magnet, will rest in no particular direction. Like we have seen in the previous question, when we demagnetize a bar magnet and suspend the same, it will come to rest in no particular direction. So this is what the explanations look like. Suspend both magnets in turn using cotton thread and wooden stands. Allow the bar magnet to swing freely in a horizontal plane. Give it time and observe the direction in which it comes to rest. The magnet comes to rest, that is the bar which is a magnet, comes to rest with one of the ends pointing in the north direction of the earth, or pointing in the north-south direction. The admagnetized bar does not settle in any particular direction. And the answer to that was just as simple as that. Let's look at part C. This one is on electromagnetic induction. We are told that figure 12 shows two identical copper coils, X and Y, placed close to each other. I forgot to name. This is X and this is Y. Coil X is connected to a DC power supply. You can see this one is a battery, while coil Y is connected to a galvanometer. They're just close to each other. Explain what is observed on the galvanometer when the switch is closed. This question is about electromagnetic induction. In fact, it's about mutual induction. When the current in coil X is switched on, that current takes time to grow or to build or to increase from 0 to a maximum value. When it builds from 0 to a maximum value, the magnetic field in the coil, because now that coil, which is carrying current, is an electromagnet, the magnetic field is going also to build outwards. It's going to increase. It's going to change. That changing magnetic field in coil X is going to cut the turns of coil Y. What will happen when that changing magnetic field cuts the coils of turn Y, of coil Y? It's going to induce an EMF in coil Y. And because the ends of this coil are connected together via a galvanometer, that induced EMF will cause induced current to flow through the galvanometer. Hence, the galvanometer will deflect. Now, when that current in coil X reaches maximum value, the magnetic field due to it does not change. So there is no more electromagnetic induction in coil Y. No more EMF is being induced in coil Y. And therefore, the pointer comes back to the center of the scale or it comes back to 0, because galvanometers usually have got a point at the center of the scale. So it can deflect in one direction, come back, deflect in the opposite direction, and then come back. But this time, it just deflects in one direction and then comes back. That is the explanation we are asked to give. So first of all, we make the observation that the galvanometer deflects to one side and then comes back to 0. And then the explanation is as I have described. So over here, I've given you quite a detailed explanation. In the exam, you might want to think about the most important points, because the space may not be enough for you to write a lot. When you're given questions with explanations and bulk marks as given there, you've got to think about each of the points that you mention earns you a mark. For example, an observation will earn you 1 mark. The galvanometer deflects in one direction and comes back to 0. That would be 1 mark. When the switch is closed, current in coil 1 increases from 0 to a maximum value. Magnetic field around coil X increases or builds up. The changing magnetic field. You must mention the idea of the fact that the magnetic field in coil X is changing. The changing magnetic field in X cuts the turns of coil Y, inducing an EMF in it, which in turn causes an induced current to flow. Then, hence the deflection of the galvanometer, because it detects this induced current. When current has reached maximum value, the magnetic field does not increase any further. There is no more EMF induced, hence no induced current in coil Y. The deflection therefore falls back to 0. That one is a detailed explanation. If you can be able to summarize it, the better. And remember, in situations where you were asked to write down factors or explanations, something like that, it's important that you make your handwriting to be legible. Don't make your handwriting to be difficult for the examiner to read. For my case here, I just typed this answer, and that is why it appears to be so neat. But for you, you will be writing with your hand. So ensure that your handwriting is as clear as possible. So let's look at part 2 of C, where we are asked to state what is observed on the galvanometer when the switch is opened. When the switch is opened, we find that the galvanometer deflects in the opposite direction and then comes back to 0. The idea of deflecting in the opposite direction is important. Okay? So, it deflects in the opposite direction and then comes back to 0. Let's look at part 3. State what is observed on the galvanometer if the number of turns in the coil Y is doubled. Again here, we're going to see that the deflection of the galvanometer will be doubled, or it will increase. It will increase because the amount of EMF induced in coil Y is going to increase. It is the amount of the deflection of the galvanometer will be doubled because the induced EMF has been doubled. The induced EMF has been doubled. So this one is supposed to be for just 1 mark. Yes, just 1 mark. This one should be for 1 mark. State what is observed on the galvanometer if the number of turns in coil Y is doubled. Yes, the deflection of the galvanometer will be doubled. So that's it about question 18. Let's go to question 19. So here we are at question 19. This question is on radioactivity and photoelectric effect. And they start by asking us to define half-life as used in radioactivity. Half-life is the time taken by the number of radioactive nuclides present in a sample to reduce to half its original value. When that happens, since the activity of an element or a sample is directly proportional to the number of radioactive nuclides present, so we can also define a half-life as the time taken for the activity of a given sample to reduce to half its original activity. So those two ways, they can be used to define half-life. However, let's stick to the standard definition of half-life, the time taken for half the number of radioactive nuclides initially present in a radioactive sample to decay. Right, let's look at part B. In part B, it's a method of detection of radioactivity. Figure 13 shows a device used to detect radioactivity by forming tracks when air is ionized. We want to know, state the name of the device shown. This device is referred to as an expansion cloud chamber. Expansion cloud chamber. This is how it works. This is the radioactive sample. It emits radiation. That radiation is going to ionize this air here, or if it is maybe moisture, alcohol, moisture, it's going to ionize the molecules here. Let's suppose that it is air molecules. It's going to ionize the air molecules. And then at the same time, this piston will move downwards, causing the air to expand. When the air expands, it's going to cool down. And when it cools down, the moisture is going to condense around the ionized air particles inside here. And therefore, it's going to render them visible. And therefore, the track, that track will clearly be seen. That's how it works. So let's look at the next question. State how the air in the device gets ionized. I've already explained that. When the radioactive element emits radiation into the chamber, the air inside is ionized. So we want to explain how this happens. The radiation removes electrons from neutral air molecules, thus making them to get ionized. When a neutral air molecule loses an electron, it becomes positively charged. If a neutral air molecule gains an electron, it becomes negatively charged. So, if radiation is a beta particle, the electron, which is actually the beta particle, attaches itself onto a neutral air molecule, thus making it to be negatively charged. For the other radiation, such as the alpha particles are going to reap electrons from neutral air molecules and make them positively charged. So that is how the air gets charged. Let's look at the next question. Number 3, describe how the tracks are formed. I've already explained this. When the air gets ionized, in other words, when the air molecules here become charged particles by the radiation, simultaneously the piston moves down, making the air inside here to expand and cool down. The moisture is going to condense around, because over here we've got vapor, inside here we've got vapor. That vapor is going to condense around the ionized gas particles, and this will make them appear to be like clouds, like smoke. So it will make the tracks or the path of the radiations visible. And that's how it works. Let's look at the points. After the air gets ionized and the piston is now moved down, suddenly air in the chamber will expand and cooling occurs. That's very important. The air inside expands because the volume has increased. The air expands, it cools down. Once it cools down, what happens? When this happens, the ions formed act as nuclei on which the saturated alcohol or water vapor condenses. So the water vapor, you find that over here there is vapor inside here. So that vapor, whether it is alcohol vapor or water vapor, is going to condense around those charged air molecules, and therefore rendering them visible, and therefore their tracks can be seen. Next, part C. This one is on photoelectrons, photoelectricity, or photoelectric effect. State two factors that determine the speed of photoelectrons emitted from the metal surface. Of course, one of them is the energy of the incident radiation, which is determined by the frequency of the incident radiation. When the frequency is high, then the energy of the incident radiation is going to be high, and therefore the electrons emitted are going to be emitted with high speed. High speed. How is that possible? The energy of the incident radiation is used to provide the work function of the metal, and because the work function has a constant value, the greater the energy of the incident radiation, the more will be the excess energy which remains after the work function has been provided. This excess energy is converted into the kinetic energy of the emitted electrons. That is how the speed of the photoelectrons emitted, of the photoelectrons which are emitted, can either be increased or decreased. We increase their speeds by increasing the energy of the incident radiation. Another way of increasing the speed of the emitted electrons, or to vary the speed of the emitted electrons, is to increase the potential between the anode and the cathode. If the potential is such that it tends to accelerate the electrons are going to move with a higher speed if that voltage is high. But if the potential is such that it opposes the movement of the electrons by connecting the positive part of the potential to the cathode, then the speed is going to be reduced. Either way, you can see that the potential across the anode and the cathode affects the speed of the emitted photoelectrons as well as the energy of the incident radiation. So here, there are those 2 points: the energy of the incident radiation. Increasing the frequency of the incident radiation increases the energy of the incident radiation, which in turn increases the speed of the emitted photoelectrons, because the excess energy above the work function of the metal is converted into kinetic energy of the electrons. So the more the energy of the incident radiation, the more will be the excess energy. And of course, number 2 is the potential difference between the cathode and the anode, which I have already explained. Another factor which affects the speed of emitted electrons is the position of the electron in the metal. You know that electron in the metal, when it gets emitted, this is what happens. This is the metal surface. Assume this is the metal surface. There is that energy of the incident radiation, which is HF. We could have 2 electrons. We could have one electron which is closer to the metal surface here, and therefore, as soon as we subtract the work function from the energy of the incident photon, it uses the rest of it to get the kinetic energy. Now, we could have that electron in the metal like this. It is far much deeper into the metal. When this electron subtract, when we subtract the work function from this, the energy which is supposed to be given to the electron as kinetic energy is absorbed by the electron, and the electron starts moving. But on its way to the surface, because of the distances involved and because of the collisions which are likely to take place, it's going to lose some of that kinetic energy, and by the time it gets to the surface, it doesn't have a lot of kinetic energy. So it leaves the metal surface with less kinetic energy. And because kinetic energy is given by a half mass of the electron times the speed of the electron squared, you can see that the speed of the electron is determined by the amount of kinetic energy which eventually it has at this point. And that is why the position of the electron in the metal also determines how much kinetic energy that electron is going to leave the metal with, and hence the speed, because we are looking at factors that determine or affect the speed of the photoelectron emitted from a metal surface. So we could also add that third point. Let's look at part C, part 2, where we are told the energy of a photon of light is 2.21 electron volts. And we are told that 1 electron volt is 1.6 by 10 raised to the power 19 joules, and the Planck's constant is 6.63 by 10 raised to minus 34 joule seconds. We are asked to express the energy of the photoelectron in joules. And this is how we do it. So we are going to say that 2.21 electron volts is the same as 2.21. We multiply that by 1.6 by 10 raised to the power minus 19 joules. And this is going to give me, I'm just going to multiply 2.21 by 1.6 because I know the power remains the same. So this one becomes 3.536 by 10 raised to the power minus 19 joules. That's how I convert electron volts into joules. You just need to multiply by the value of the electronic charge, which is 1.6 by 10 raised to my power minus 19 joules. Then part 2, that was part 1. Part 2, we are supposed to determine the frequency of light that produces the photon. The energy of this photon is given by hf, where f is the frequency, h is a Planck's constant, and E is the energy. We've already worked out this energy, so the frequency is going to be equal to the energy divided by Planck's constant. So the energy is 3.536 by 10 raised to the power minus 19 joules, while Planck's constant is 6.63 by 10 minus 34 joules seconds. You can see that joules and joules are going to cancel out, and the answer we are going to get will be in per second, which is the SI unit of frequency. So what I'm going to do, I'm just going to divide 3.536, I divide by 6.63, and that gives me 0.533, 0.533 by 10 raised to power. There is a 34. When 34 now becomes a numerator, it becomes positive, and I have to subtract 19, and I get to power 15 per second. And this implies this is like 5.33 by 10 raised to power 14 Hertz. And that is how we work out the frequency of the light that produces the photons. And that brings us to the end of this paper. It has been quite a long paper. I'd like to encourage you, if you are not a member of my channel yet, go ahead, subscribe, because this is the way I've decided to be looking at these past papers. I look at a complete paper. It may be long, yes, but I've also given you an opportunity to go to the question of your choice. I've provided you with the timestamps for each question. If you put your cursor over the scroll bar, you'll be able to identify various questions that you're interested in. Go directly to those questions. If, for instance, you find maybe question number 2 is much easier, it's not worth checking, you go to the question of your choice. Although initially, I will encourage you to go through the whole paper. I want to thank you for having the patience to go through this over 2-hour video, and I have no doubt that it has benefited you. Go right ahead, leave some comments below this particular video, share it with your friends, and if you're not a member of my channel, just take time and subscribe, because there is a lot that you learn when you are a member of this channel. Otherwise, goodbye until next time when I come up with another past paper.